Hey everybody, I'm Garrett Ray. Thanks for tuning in to my presentation of my research project I've been doing for the winter 2021 semester called Assessment of Asymmetric Sampling Delay in Per-Phase Current and Position in Permanent Magnet Synchronous Machine Controls. So I know that was a lot to take in. If you're new to motor controls or electrical engineering in general, that's okay. I'll explain it all as we go on. So the purpose of this research is to gain a thorough understanding of how asymmetric sampling delay in three-phase current feedback and position measurement affects the stability of field-oriented controlled permanent magnet synchronous machines. And the reason we're doing this is to hopefully lead into further research and investigations to design and understand and develop smart control algorithms and motor control fault detection systems. So what are permanent magnet synchronous machines? What is this large term I've been using? Well, first of all, we can shorten it to PMSMs. They're one of the most commonplace types of AC motors in the modern day. They are operated by inducing a rotating magnetic field onto the rotor's permanent magnets using AC current. So what happens, you can see in the second picture there, we have an exposed PMSM with its three-phase windings and its opposite three-phase windings as well. So what happens is we pass AC current through those windings, and though that AC current induces a magnetic field onto the rotor, and that magnetic field rotates, and the rotor, you can think of it, will magnetically latch on to that field. So as that field rotates, so too will the rotor, and thus you get rotation of the motor. And the rotor speed is proportional to the electrical frequency that's applied. So the electrical frequency obviously will directly affect the rotational speed of the field, and that will be proportional to the speed of the rotor. So why are PMSMs relevant? Well, they're used in a vast number of industries and applications. In fact, you probably come across them almost every single day and multiple times a day of your life. They're used in automotive applications like electronic assist power steering, or in electric vehicles for electrical propulsion, as that's definitely growing in this modern day. They're used heavily in robotics for their precise operation and high torque output. They're also used in machine tooling with their very high speeds and high torque again. And then they're also used in very, very common household products like air conditioners and refrigerators and much, much more. And they're used here because they are very, very power efficient. Okay, so we know what PMSMs are, but how are they controlled? How do we operate them? And this is where we start to go a little more into sort of the mathematical realm, and we can start to analyze how this actually works. So there are numerous ways to control PMSMs, but the way that, or one of the most common ways, and the way we'll be using it for the purposes of the research, is called field-oriented control, or FOC. It's also known as space vector modulation. And essentially what this does is it converts three-phase AC current into a two-axis DC current reference. So what we're able to do is convert three sinusoidal signals into two theoretically constant signals, just two straight lines on a graph as compared to three sinusoids overlapping each other. And you can see that in the diagram on the right side. And so this very, very heavily simplifies the controls in the efforts to control and understand the dynamics of a system that is using FOC control. So this is done mathematically through what is known as the reference frame transformation and the inverse reference frame transformation. With the reference frame transformation, you multiply what is known as the reference frame transformation matrix by the three-phase currents. After these three-phase currents and the reference frame transformation matrix have been multiplied, your result is the QD zero-axis currents. Although the zero-axis is irrelevant for most applications, and only the Q and D axes are considered. So then the inverse reference frame transformation similarly will do the opposite, where you will pass in Q, D, zero axes values into the inverse reference frame transformation matrix given there, and then your result will be three-phase values, three-phase sinusoidal values as an output. And I was going to say voltage, but realistically, this I and this V denote current and voltage. But realistically, these can be in current or voltage or vice versa. Doesn't matter. These are the reference frame transformations. So how is delay introduced? What is delay? Why does it matter? So feedback delay can occur in a PMSM system when the microcontroller that is responsible for performing the field-oriented control on the motor misses a sampling period. And this is caused by microcontrollers having high sampling frequencies, in which the sampling frequency is the number of times per second that it will read the feedback value from the feedback currents on the motor. And it's caused by them having high sampling frequencies while having a myriad of other software tasks that need to be performed following the feedback sampling. So sometimes being overloaded with different tasks to perform, they could miss a sampling frequency, or excuse me, they could miss a sample period, and thus you have delay introduced into the system. However, this is currently a very rare phenomenon because, well, people are aware of delay, and delay is very undesirable. And so generally motor controls engineers will prioritize their motor control routines very highly, and so that they rarely ever miss a sample period. So why is the delay effect important? Why do we care? Well, sampling delay is a very, very undesirable phenomenon in motor controls. It causes a lot of system instability, such as current harmonics, and that leads to torque ripple. So essentially what that means is your torque becomes unstable, and thus your speed could become unstable, and the system just won't work properly, won't work how you expect, and that is very obviously undesirable. So, at SDSU, we have had a precursor project that this is actually following up on. In this project, called Feedback Path Delay Effect on Stability of Controlled PMSMs, a similar effect was investigated. However, there was symmetric delay on 3 phases, as opposed to this research, which will investigate various combinations of non-equivalent delay compared to the previous one, where the delay on the current phases were equal. This project will analyze various combinations of non-equal delay on the measurement paths, which means that we're going to analyze delay, varying levels of delay simultaneously on the 3-phase feedback, or excuse me, 3-phase current feedback and position measurements. So how have we approached this research? So first of all, we need to mathematically analyze the system. So to do that, we've evaluated the closed-loop frequency domain behavior of the system. And to do this, we've collected the closed-loop transfer function in a matrix form. And then we collect Bode plots of the system with varying system parameters such as sampling frequency and controller bandwidth. And then for simulation, we've modeled the PMSM in Simulink. And using this, we can simulate the system, and we can retrieve the step response of the Q-axis current while injecting varying levels of delays in the feedback current and the position reading. For our experimental setup, we've set up 2 Texas Instrument PMSM controller kits with a dual PMSM dyno. Essentially, this means there are 2 motors that are hooked, their rotors are hooked onto each other. One motor controls the speed, and the other motor controls the torque of the system. And then to achieve and to analyze this, the results for this research, we need to alter the field-oriented control software to behave the way we want to and to inject measurement delay into the system. And then from here, we will collect and analyze current step responses from the system and maybe a few other results. So for the mathematical analysis, from a high level, we wanted to develop a closed-loop transfer function of the system. And from a high level and just theoretical control system analysis, this is the generic equation or the generic setup of a closed-loop system. So we have some command given in x of s, which is then sent through to the forward path G of S, which would usually contain our controller and our plant, or our motor in this instance. And then it would achieve some sort of an output. In this case, it would be our three-phase current. That current would then be fed back into the feedback path, which would then be passed through, again, the feedback path, H of S. And then that would be brought back into the forward path, and the value would be controlled for in the system. So this is a high-level approach, and then this can be broken down in our application, in this next slide here. So this is broken down into a little more detail, where we can see we have I star of S, which would be our reference currents, which would be our IQ or our ID. And then that would be passed on to C of S, which is our PI controller. The result of our controlled currents would be a Q and D axis voltage, which would then be passed in through M1, which is the inverse reference frame transformation as mentioned earlier. This would then give us three-phase voltage, which would then be used to directly command the motor. And after commanding the motor, we would retrieve a current feedback in the form of IS here in this diagram. This current feedback would then be brought back down into the feedback path, as well as output into the system. But it would be brought down to the feedback path, pass through our delay matrix, which in this is represented here as D. This delayed three-phase current would then be passed through M2, which is the reference frame transformation, and then we would achieve our QD axis current feedback, which would then be used in the loop again and would be controlled to just achieve field-oriented control. And this can be seen mathematically modeled as the frequency domain transfer function on the right side there, where you have I of S over I star of S. For simulation, the PMSM system was modeled in Simulink. So you can see here it starts off with the IQ reference passed through a controller, and then it is passed through the inverse reference frame transformation to achieve our three-phase voltage, which is then passed into the PMSM system, which then we will get our three-phase current feedback as well as our position measurement, and then this would be used to once again transform our three-phase current into our DC IQ and ID currents. And then again, as we can see, that I0 current isn't used in this application. So here are some examples of the results of our simulation. So in this setup, we are varying the sampling frequency of the system, and we have, for all three of these examples, we have the same delay, where phase A is delayed by 10 samples, phase B is delayed by 5 samples, phase C has no sampling delay, and position also has no sampling delay. And the controller bandwidth is set to 200 Hertz. So you can see that the 5 kilohertz sampling frequency reacts very heavily. You can see quite a bit of instability in the system initially. So it reacts quite strongly to the asymmetric delay. The 10 kilohertz sampling frequency system, again met with the same amount of sampling delay, is able to respond a little faster, a little better, and a little more robust to the delay. And then we can see over on the right side the 20 kilohertz sampling frequency is able to respond very quickly and very, very robustly to the sample delay. So for the experimental results and the experimental setup, we've set up again the Texas Instruments devices and the controller boards and the PMSM motors themselves. And we've also set up the software to perform field-oriented control. I was going to show you a video, but unfortunately my PowerPoint was crashing every single time I would try to embed the video into the slides. So this was a video here of the motor spinning in an open loop setup, so not closed loop. So this is just commanding a voltage to the motor and letting it spin. It doesn't have any form of current control. You can see on the left side, it's plugged into the board and plugged into our 30-volt power supply and spinning. And then you can also see on the oscilloscope on the right side, What you see in the green is essentially a representation of the rotor position, and then in the yellow is the electrical position. So in conclusion, so far through our analysis, we have found that asymmetric delay propagates through the entire PMSM control system, and it affects nearly every aspect of its computation. In our simulations, we have found that even delay in a single phase can cause system instability. And this is a novel finding compared to the previous research where symmetric delay in 3 phases was analyzed. Well, now we found that even delay in a single phase can severely destabilize a controlled PMSM system. Our current progress, we have completed and obtained the closed-loop transfer function of the system. We still have yet to collect the Bode plots and frequency domain results. For simulation, we have completed the model and we have our first set of single-phase delayed simulation results. However, based on this, we need to configure more tests and simulate more combinations of delay in phase and position feedback or measurement. For our experimental progress, the hardware setup is completed and some initial software setup is done. However, software needs yet to be altered to meet the needs of this experimental setup to inject delay and collect the results we're looking for. We are planning to publish the findings of this research to an IEEE conference, so hopefully we can find some good results. And finally, some acknowledgments. I would like to thank SVSU UGRP for funding this project. It's been a huge help, obviously. It would have been extremely hard to pull this off without that financial support, so thank you so much. And then I would also like to thank the project advisor, Dr. Sandun Kuruppu. He's been an incredible mentor, very, very patient, very wise. It's been very, very fun, very enjoyable and interesting experience so far. So thank you. And thank you so much for watching.